In the last lesson, we started to look at uniform circular motion. When an object moves around in a circular path at a steady speed, and the circular path is a fixed radius. And we considered what forces must be acting on it. There must be a centripetal force, a force acting towards the center of the circle, and it would have a uniform angular velocity and a uniform linear velocity. The linear velocity being the speed around the outside. It's important to remember that when we talk about velocity in this case, we're not too concerned with the fact that it's changing direction all the time. The linear velocity is really the speed, sometimes known as the tangential velocity. Let's consider circular motion in this case. Here I've got a plug hanging from its cord, and if I swing that round in a sort of cone shape, the plug is moving in uniform circular motion. But what forces are acting on it? There's the tension of the cord pulling up towards my hand. There's gravity pulling it down. The gravity obviously only works downwards. The tension has an upwards component and a sideways component, a horizontal component. And the horizontal component is what's providing the centripetal force to go in a circle. The vertical component is counteracting gravity. So let's have a look and see, can we put these together with some equations. Here we have our conical pendulum, just like we had in the video. We've got our mass, which is moving round in a circle, and the radius of that circle is r. There's a tension pulling up towards the hand, and the tension can be resolved into two directions. Horizontally, it's going to be t cos theta, and vertically, it's going to be t sine theta, where theta is the angle between the string and the horizontal. So this horizontal component, t cos theta, that's what's going to be providing the centripetal force to move it around in the circle. And we know that centripetal force is equal to mv squared over r. It can also be equal to mr omega squared. The vertical component of tension is going to be t sine theta. And because the pendulum is moving in a horizontal circle, the object's not moving up or down, we know by Newton's first law of motion that the vertical forces must resolve to zero. There must be zero resultant force. So the upwards force, t sine theta, will equal the downwards force, mg. So if we wanted to find out what theta was, we need to solve these two simultaneous equations. T cos theta equals mv squared over r, and t sine theta equals mg. Now to do that, we need to know one useful trigonometric function, and that is that sine theta divided by cos theta equals tan theta. So let's call this equation 2 and this equation 1. If I divide equation 2 by equation 1, I get, well, t sine theta over t cos theta. The t's are going to cancel out. That's going to equal tan theta. Sine theta over cos theta equals tan theta. And if we were to substitute in the right-hand side of those equations, we would get mg over mv squared over r. And if we were to simplify that, the m's will cancel out. We get gr over v squared. That's going to equal tan theta. Is it possible for the object to move perfectly horizontally? In other words, is it possible for theta to be zero? Or at what speed must the ball be going for theta to equal zero? For theta to be zero, tan theta must also be zero, which means v squared must be infinite. Really, it has to be moving at an infinite speed to get horizontal. That's not possible. I'm sure you can imagine as you spin something faster, it's going to move higher and higher. But it can never be perfectly horizontal, because there's always a downwards component of weight. If the string got to a horizontal position, all the tension would be horizontal. There would be no vertical component of tension. But weight would still exist, and the weight would act downwards, so there would be a resultant force. That would be downwards, and it would pull the object downwards, and the string would not be horizontal. So if we ignore any sort of aerodynamic effects, it is impossible to spin the ball fast enough to get the string absolutely horizontal, because there's always a downward component of weight and we need an upward component of tension to counteract that. Previously we saw that the size of the tension must remain constant. The vertical component of the tension equaled the downward component of gravity, and the horizontal component of the tension was the centripetal force. Obviously it changed direction, but it always acted towards the centre of that virtual circle. What happens if we have a vertical circle? So if we swing something vertically, so it's going straight up and down, a bit like a roller coaster doing a loop-the-loop. Well, can you think, is the tension the same the whole way around? Well, for me it feels a bit tougher whenever it's at the bottom of the circle. Let's see what happens now. This might seem a little bit harder to get your head around at first, but if you keep a few things in mind, you should be able to get through this. So, we've got an object of mass m. It's going around in this clockwise direction, but it's a vertical circle. The string is length L, so that's the radius of the circle. And the mass is constant, so the weight is also constant. It's also important to remember that we're considering this is moving at a constant angular velocity. So really, omega is constant. If omega is constant, v is also constant, which means the centripetal acceleration is also constant. So that's the important thing. It also means that the centripetal force is constant. And that's the key thing here. The centripetal force at all times is constant to keep this moving at a steady speed. Now, we've got the mass, and the mass is producing a weight, and that's acting downwards at all times. So I'm going to put this in the diagram. mg, g. So the mass is always acting downwards. The tension is also acting in towards the centre. But the tension is going to change. If you can imagine looping something round in a circle, it feels a bit lighter going over the top of your hand and a bit heavier coming down the top at the bottom. And that's because at the top the tension is smaller, and at the bottom the tension is higher. So I'm going to call the tension T, and I'll call it T1, T2, T3 and T4. And so we're just going to consider the tension at these 4 points around the circle. At the highest point, the lowest point, and 2 horizontal points. So, important things to remember. The centripetal force causing the motion is F equals mv squared over r. And that is going to be constant throughout the whole path of the circle. And that force is going to be the resultant force of the tension and the weight. So that's the important thing to remember. The centripetal force is produced by some combination of the tension and the weight. And we're only interested in what's going in towards the centre of the circle. So let's consider at A. The top there. The tension is acting towards the centre. The mass is also acting towards the centre. So, F equals mv squared over r, and that's going to equal T1 plus mg. They're both acting in the same direction, and they're both acting in the same direction as the centripetal force. I could rearrange that and say that T1 is equal to mv squared over r, take away mg. So really, the weight is helping out the tension there. It's taking up some of the force that would otherwise have to be produced by tension. At B, the weight is perpendicular to the tension, so the weight has no component towards the centre of the circle. So the weight has no contribution whatsoever to the centripetal force. So F equals mv squared over r, and that's going to equal T2. Because the weight has nothing to do with it. The weight has 90 degrees to it. If we resolve through 90 degrees, you get cos 90, which is 0. There is no component of the weight in the centripetal direction. So T2 equals mv squared over r. At C, at the bottom of the circle, the tension's pulling up, the weight's pulling against it, and we need a bigger tension because the tension has to both provide the centripetal force and counteract the weight. So in this case, F equals mv squared over r, and that's going to equal T3 take away mg, because they are in opposite directions. T3 equals mv squared over r plus mg. So the tension is equal to the centripetal force plus the weight. And then D, it's going to be very similar to B, but in the opposite direction. Again, the weight has no component in the direction of the tension, and it's got no component towards the centre. So F equals mv squared over r again, which is equal to T4. So T4 equals mv squared over r. So following through in our notes, at points B and D, the weight of the object is at right angles to the string. The weight does not contribute to the centripetal force. So in other words, the tension equals the centripetal force at B and at D. As the object moves from A to B, in other words, from the top of the motion, down to the side and down to the bottom, the tension is going to increase. We can see here at A, the tension is mv squared over r take away mg, and at the bottom, at C, it's mv squared over r plus mg. So it's going to increase. And on the way back up, from C back to D back to A, it's going to decrease. It occurred to me we haven't written down that this is A, B, C, and D. It's a sinusoidal pattern. So if we were to plot a graph of tension around the circle, at the top we'd have a minimum, and it would increase and decrease sinusoidally. That's at A, B, C, D, where that point is equal to mv squared over r, mv squared over r take away mg, mv squared over r plus mg. If the string was going to snap, where is it most likely to snap? It's going to snap at the bottom because that's where tension is highest. We can also consider what's the minimum speed required to make something make a complete loop. If we consider here, as the object is moving around, we know the tension is changing. It needs to keep this constant centripetal force, mv squared over r. At the top, at A, we know the tension equals mv squared over r minus mg. So if mg is ever bigger than mv squared over r, it would produce a negative tension. In other words, it would start to fall in towards the centre, which doesn't really, which means it won't keep going in a circle. It'll fall out of the loop. So if something is going to make it, you cannot go any slower than mv squared over r equals mg. If we say mv squared over r equals mg, that is true when the tension goes to 0. In other words, it's just about making it over the top of the circle. If mg was any bigger than that, it would start to decrease the radius. It would fall in. So this is key to think about how fast does a car need to go to make a loop-the-loop in a roller coaster. So if the v was any smaller, the car would fall. We can also use this to think, let's say a car is going over a bridge. If it goes too fast, it's going to jump. And generally you don't want that to happen in a car. So we can use this to work out what is the maximum speed a car can go over a lump in the road without it taking off. We can treat the lump as a circle. We know the radius. We know the car's mass and weight, mg. And again, we can just put the limiting factor of mg equals mv squared over r. Because mv squared over r is mg and mg is a constant, if v is too large, r has to increase. In other words, if it's a larger circle, in other words, it leaves the road. So, to consider when a roller coaster will drop out of its track, or if a car will leave the road, we need to remember mg equals mv squared over r, and that is our limiting factor.